Okay, so I want to talk a little bit more about nutrients and where they come from before we move on to other types of pollution. So we're going to talk about nitrogen in particular. Nitrogen comes from intensive agriculture and industry, and we have dramatically altered the nitrogen cycle on planet Earth. And so nitrogen has historically been very limited. There is a lot of nitrogen in the air in the form of nitrogen gas, which you can see here is N2. And some of you may remember from chemistry class what's special about N2. It has a particular type of bond that makes it very unavailable, even though there's tons of it in the air. The answer is that it has a triple bond. So a regular chemical bond usually can be broken and reformed. So a single bond is relatively easy to break and reform. A double bond is very hard to break and reform. A triple bond is almost impossible to break. It takes so much energy to break a triple bond that it doesn't happen very commonly in nature. So there's a few different ways, and so we call this nitrogen fixation. It is the conversion of this nitrogen in the air with the triple bond to something that's usable. We want something that only has like a single bond so that organisms can actually use it in their tissues, and protein has lots of nitrogen in it. So the reason you eat lots of protein when you want to build muscles is because there's all that nitrogen in there that you need in order to build muscles. And so all organisms need nitrogen. So it's called nitrogen fixation if we take it from the air in the pretty much unusable form and turned it into something that's more reactive and usable. So we can see here, these are the non-human sources of nitrogen fixation. Most of it comes from terrestrial nitrogen fixation. So these are organisms that can break up this triple bond. They're called nitrogen fixers, and some of them have relationships with plants. So we think of legumes, things like soybeans. This is the reason we rotate crops between soybeans and corn, because soybean has a special relationship with a microorganism that can fix nitrogen and make it more available. And so then there's more nitrogen in the soil, and then we rotate and put corn in that will use the nitrogen from the soybeans. So terrestrial fixation is just natural plants in ecosystems that have this relationship with microorganisms that can make nitrogen available. The other way is marine fixation. So there are some types of blue-green algae that can fix nitrogen. And then we also get some fixation from lightning. So I said that it takes a lot of energy. Well, lightning has a lot of energy and it'll break the bonds in the air that it goes through. These are the human-related sources. And so we see yellow are the crops. So this is mostly those soybeans that we're planting to fix nitrogen for us. This is industrial fixation. This is fertilizer production. And so we learned how to do this by burning lots and lots of fossil fuels to take the nitrogen out of the air and make it available. So that's how we make industrial fertilizers. And then the red is burning fossil fuels. So when combustion occurs, that's a lot of energy, and and nitrogen can be fixed in that process as well. And so what we see is that all of the sources of human fixation are higher in total than all of the non-human in our natural ecosystems of nitrogen fixation. This shows the delivery of total nitrogen in different areas, in different watersheds. And you can see a lot of the black is here. And this is the corn belt. This is where we grow tons and tons of corn. And we put lots of fertilizer on there, or we sometimes rotate with soybeans. The next type of pollution I want to talk about is air pollution. And a lot of this comes from combustion of fossil fuels. That creates nitrogen gas, water vapor, carbon dioxide, nitric oxide, sulfur dioxide, And 3 of these are greenhouse gases. And some of these are things that cause acid rain. So carbon dioxide, nitric oxide, and sulfur oxides, when they're combined with water, they create an acid. So we get carbonic acid from carbon dioxide dissolved in water, nitric acid from the nitric oxides dissolved in water, and sulfuric acid when sulfur dioxide combines with water. And if you'll remember from chemistry class, sulfuric acid is a particularly strong acid with a very low pH. And that one is one that we've kind of worked on with different regulations in the United States. So those cause acid rain. So if those things are up in the air, when clouds are forming, the water droplets get these different contaminants in them, creating the acid, and it decreases the pH of our rainwater, causing more acidity and problems with plant growth and some other problems. So this shows sulfur dioxide emissions between 1940 and 1988. It also shows nitrous oxides changes through that time as well. And we see that nitric oxides are formed by oxidation of atmospheric acid during burning of fossil fuels. This happens in car engines as well, so not just in factories. And we said it makes an acid when it combines with water. Sulfur comes primarily from fossil fuels, especially coal, and sulfuric acid is created when sulfur dioxide combines with water. And so we can see here that the Clean Air Act was enacted in 1970, and that's when our emissions of sulfur dioxide started decreasing. But you can see from the 1950s to about 1970, it was increasing dramatically. And then when we took action, it's gone down quite a bit since that high in around 1970. So Clean Air Act is the cause of this decline. So these regulations are actually pretty effective, and so the amount of acid rain has gone down in conjunction with decreasing sulfur dioxide emissions. This looks at the pH of precipitation. So if you'll remember back from chemistry class, a pH of 7 is neutral. And if it's lower than 7, that means it's acidic. So you can see here, normal rain has a pH of about 5.6. So the green parts are close to a normal pH of rain. The red, which gets down to pHs in the 4s, is much more acidic than what rain would typically be. And you can see that most of this is in the northeast of the United States, where we have more people, more traffic, more factories. So why is acid precipitation harmful? Well, some organisms have different tolerances for different pH levels. So it can slow the growth and development. It can change decomposition rates, slowing it down, and it can kill some organisms as well. So it also leaches heavy metals from the soil and makes them more available. So aluminum toxicity and mercury toxicity are much more likely if there's a lot of acid precipitation in an area. And it particularly is harmful for things that have a shell. So mollusks, things like snails, clams, crayfish, corals are particularly susceptible to changes in pH. But basically they can't form their shells, or their shells start dissolving if the pH is too low, if there's too much acid. For air pollution, we also see that it crosses boundaries a lot, and so this shows areas with acid precipitation and areas where that's transported just by air currents. And so as The acid rain might be created in clouds above a certain area, but because wind currents or prevailing winds go in particular directions, they can affect places that didn't even have any factories.